Hello everyone, my name is Kalia and today I will be teaching you about the equilibrium constant and Le Chatelier's principle. The equilibrium constant is represented by the letter K, and it indicates the ratio of products to reactants at equilibrium. When measuring concentrations, the K value has a subscript C and is calculated by the equilibrium concentrations of each product to the power of their stoichiometric coefficients, divided by the equilibrium concentrations of each reactant to the power of their stoichiometric coefficients. When measuring gas pressure, there's a subscript P, and the K value is calculated in the same way, except the equilibrium concentrations are replaced with the equilibrium partial pressures. However, this formula only applies if all species in a reaction are in the same state. Using this example, which will be our case study example later on, we can write the Kc and Kp expressions. For concentrations, Kc is the concentration of sulfur trioxide squared, divided by the concentration of oxygen and the concentration of sulfur dioxide squared. For pressures, the Kp is the partial pressure of sulfur trioxide squared, divided by the partial pressure of oxygen and the partial pressure of sulfur dioxide squared. When there are multiple states in a reaction, you must calculate the activity of each species. For aqueous species, this is done by dividing the equilibrium concentration by the standard concentration of 1 mole per liter. For gas species, this is done by dividing the equilibrium partial pressure by the standard pressure of 1 bar. The activities for a solid and liquid state species is just 1, and thus solids and liquids do not appear in the K expression. Another feature of the equilibrium constant, although it may seem self-explanatory, is that it's always constant, meaning that no matter the starting concentrations, the ratio of products to reactants at equilibrium will always remain the same. To demonstrate this, we will look at two experiments of a case study example that we used briefly earlier. Sulfur dioxide is released during eruptions of volcanoes. It rises into the atmosphere and reacts with oxygen to form sulfur trioxide. Sulfur trioxide will react with water further up in the atmosphere to produce acid rain. In experiment 1, the starting concentrations are 2.116, 1.158, and 0 respectively. The equilibrium concentrations are 0.2, 0.1, and 1.058 respectively. Using the equilibrium concentrations, we can calculate the equilibrium constant with the expression we wrote earlier. This results in a Kc of 280 at a temperature of 1000 degrees Kelvin. This is a very large K value, meaning the forward reaction is favored, and there will be a lot more products than reactants at equilibrium. If a K value is small, the reverse reaction is favored, and there will be more reactants than products at equilibrium. In experiment 2, the starting concentrations are 0.45, 0.5, and 0.0582 respectively. The equilibrium concentrations are 0.05, 0.3, and 0.4582 respectively. Once again, using the equilibrium concentrations, we can calculate the equilibrium constant. This results in a Kc of 280 at a temperature of 1000 degrees Kelvin, demonstrating that no matter the starting concentrations or pressures, the equilibrium constant will remain the same. We can see this concept in a graph showing the concentration of each reaction species as time progresses. Equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. In the graph, equilibrium is reached when the lines flatten. As you can see, no matter what concentrations we start with, an equilibrium will be reached and K will remain constant. Although the final concentrations of a species is the same between both graphs, they do not have to be. This was proven in the previous experiments. In addition to K, which tells us the ratio of products to reactants at equilibrium, the reaction quotient, represented by Q, tells us the ratio of products to reactants at any time in the reaction. Q is calculated in the same method as K, however the concentrations or pressure will not be at equilibrium. We can compare the Q at a point in the reaction to K in order to determine which direction the reaction will proceed in. If Q is larger than K, there are more products at this time than there will be at equilibrium, and therefore the reverse reaction is favored. If Q is equal to K, the reaction is at equilibrium. If Q is smaller than K, there are more reactants at this time than there will be at equilibrium, and therefore the forward reaction is favored. We can apply this concept to our case study example when at some point during the reaction the concentrations are as shown, 0.095, 0.45, and 0.815 respectively. In calculating Q, we obtain a value of 163.5. This is less than the K value of 280. More products and less reactants are needed to reach equilibrium, and therefore the forward reaction is favored. Le Chatelier's principle states that when a system experiences a disturbance, the reaction will respond by shifting in a direction to try and counteract the change. Disturbances could include concentration, pressure and volume, or temperature changes. First, we will look at the concentration effect. If reactants are increased, the reaction will counteract and shift to the right to produce more products and restore equilibrium. If the products are instead increased, the reaction will counteract and shift to the left to produce more reactants and restore equilibrium. Decreasing reactants will follow the same trend as if you were increasing products. As well, decreasing products will follow the same trend as if you were increasing reactants. Next, we will look at the pressure effect. If pressure is increased, which can also be done by decreasing volume, the reaction will counteract by shifting to the side with less moles to restore equilibrium. If pressure is decreased, which can also be done by increasing volume, the reaction will shift to the side with the most moles. In our example, when pressure is increased, the reaction shifts to the products, as the product side has less moles than the reactant side. Finally, we will look at the effect temperature has on the system. Each equilibrium reaction has an endothermic and exothermic reaction. The exothermic reaction is in the direction that produces heat, and the endothermic reaction is in the direction that consumes it. If temperature is increased, the system will counteract by shifting in the direction of the endothermic reaction to try and lower the temperature. If temperature is decreased, the system will counteract by shifting in the direction of the exothermic reaction to try and increase the temperature. In our example, the forward reaction is exothermic and the reverse is endothermic. Therefore, when temperature is increased, the reaction will shift to the left. Equilibrium is present in many real-world reactions where the reactants are not completely formed into products. As we saw previously, one example is in a volcano. The sulfur dioxide released during eruptions rises and reacts with oxygen to form sulfur trioxide. This sulfur trioxide will eventually react with water in the atmosphere to produce acid rain. Equilibrium concepts can also be used in swimming pools to adjust the pH if it's too high or too low. Le Chatelier's principle can also be used in industrial processes like the Haber process, where ammonia is synthesized from nitrogen and hydrogen to obtain the highest yield of products as possible. Equilibrium also exists within our bodies. For example, oxygen binds to hemoglobin in red blood cells to be transported around our bodies. Le Chatelier's principle can be used to predict the effect and shift in equilibrium of high altitudes on our breathing, where there's low oxygen concentrations and low pressure, as well as the effect of carbon monoxide poisoning. Here are some extra practice problems to review all the concepts we have just learned. You can pause the video here and resume to see the answers when you are ready. Thanks for watching. I hope you enjoyed and learned something.